Good morning, everyone. Group 1 members comprised of Cummins and Oxwell, Katumewa Zekatubat, Makawa Mpanzi John, Owenjas and Anyamo Colin. We are presenting compressions and its applications in the industrial setup. Introduction, we are looking at compressions. Basically, compression refers to increasing pressure so as to reduce volume. And a compressor can be defined as a mechanical device that compresses the gas, because we are talking to increase pressure, and by increasing pressure we are reducing volume. So it is a mechanical device that compresses gas or liquids so that the power produced when the gas is released can be used to power another machine. So when we increase its pressure, the power we are creating is mainly meant to run the other machine. The history of compression in 1833, when Charles and Elias Cooper, the systems began when Charles and Elias Cooper established a foundry in Mount Vernon. Then in 1920, the first compressor was made by the gentleman called Ajax in Pennsylvania, and in 1955 the industrial compressor group was then formed in New York. In 1999 the rotating compressor were made that we shall see in the types and the mode of operation. Then in 2001 we see that copper energy services and copper turbo compressor combined to form the copper compression. We had seen the groups before. So they combined later to form the compressor, they form the copper compression. The nature of displacement of the compressor, we are having two natures. One is the positive displacement. Here we are mainly forcing the air or the liquid into the chamber. So we reduce volume. We are using like a shaft or a piston. You push to increase pressure, to reduce volume, and by doing that you are increasing pressure. Then the other one is negative displacement, whereby you are having something like sort of turning. It keeps turning to increase the air. If the air is passing through a liquid, it is turning it up. You are not pushing, but this time it is turning it up to accelerate or decrease that air or liquid which it is capturing, and thereby increasing its pressure. We can look at one of the colleagues can come and look at the types of the compression.
But before looking at the types of compression, we can also take a look at how the compressor works, its operation. So that's how the compressor simply operates. So what you're seeing, this you're seeing is the inlet where air or liquid is allowed into the compressor, and inside it has got what you're seeing, this you're seeing is meant to clean the air or the liquid that is getting into the compressor. What goes inside is as clean as possible. So it is always removed and then inserted again after cleaning it when it has attained some dirt. So what goes through is the air you are seeing down. That's how air enters. And what you are seeing, this one is our imperers, the so-called turning parts of the compressor. And when air is already inside, the imperers will turn, and in turning, you see, these are imperers. So they turn to keep on rotating, opening, allowing air or the liquid to go through. As it goes through, the liquid is being compressed because the volume is reduced. And This is continuous. The red things you are seeing, it is the other end process where the air has already attained high pressure, and where you are seeing sort of light blue things is the incoming air, which is at a very low pressure. So the process continues, and we shall, because we have done friction, it's also taking place, and we need to replicate and have that friction reduced. So to reduce the friction, we shall now apply some oiling, of which the oiling will reduce the friction, and that's how the oil is applied. The oil tank, the oil tank is put on top, and it keeps on. Also, the oil tubes are embedded within the system and keeps on running. As it's running, oil is being deposited on the impellers and friction is being reduced. So the first thing is to remove heat for optimal temperature. And you can see what comes out. It is a very high pressure liquid, and here it's going to the so-called discharge port, from where it can be connected to any part you want to move or anything you want to transport.
Compressors. Here are like the dynamic systems, mostly the machines which are rapidly rotating the impellers, as we have seen it from the operation. Secondly, we have the vertical split centrifugal compressor, where we have the multiple impellers which are attached to a single rotating shaft. The next one, we have the horizontal split centrifugal accelerations. This is also attached to a single rotating shaft for a multiple state structure. The next one, we continue with the axial compressors, whereby the dynamical machines are accelerated, in which the gas is flowing in the direction, converting the velocity to pressure. Second last, we have the liquid ring compressors. This is where the impellers are placed inside a tube and the centrifugal forced in the internal cavity, and the liquids form the shape producing regions of the changing volume. Then lastly, we have the sliding van compressors, where the slotted cylinder is fitted with a non-metallic vans and placed inside a tube.
And you can also look at the application in industrial sector.
Let's look at the application of compressors in an industrial sector. First, we are saying the compressors are used in vacuum pump system. Vacuum pump systems, if you want to remove air, maybe from your material, or you have gone to food and science, you saw how that thing was sealed. It was using vacuum pump, where some air has to be removed out, such that the vacuum is created. There we need to use compression, or because we can either remove or add there some air. Then we have pressure-based machines. Most of you, they have used motorcycles, even cars. Also in industries, we have those pressure-based machines. There are those machines which, whenever you want to stop them, maybe you apply some pressure somewhere, then the pressure which is transmitted, it causes the machine to come to a stop. And that one you can only do them by using compression, as you learned about pressure in your high school. And most especially, you were introduced to hydraulic press, and then most of the users of the hydraulic press. Then the next one we are saying one of the application is pressurized transport system. In the pressurized transport system, most especially when we want to transport maybe some gas from one point to another, or we want to transport a liquid from one point to another, you have taps at your home, we have taps maybe in the industry where we need some water coming out with some pressure. Well, if we don't have a compressor, we cannot successfully deliver such water at a good pressure that we need. So they need the compressors. The next one is the refrigeration process. That one we looked at it the other time when we were dealing with refrigeration, where we store a pump which was supposed to pump and then distribute those refrigerants throughout the refrigerator in order to cool something that you want. In industrial setup, we also saw some refrigerators which were meant for preservation of the products that we made. And for those who are not went to food science, we were able to see the refrigeration room. Hoping you can appreciate that. Then, lastly, I have air conditioning. In order for you maybe to maintain some room temperature that you want, then at least you also need a compressor. Why do you need a compressor? You have air inside there. Maybe you can have some air which is being blown inside the room, and then you have your room well conditioned. Then there we have a simple diagram indicating how you can use your compressors. Those red things that you can see is where you can apply your compression, and then you can see that the other first one, that one, it is gas injection. You can call it gas lifting, where you can lift the gas, and then you can also gather the gas together using compression. You can bring them together, because without compression you can't gather them. Then you can also separate these gases when you have a filter. Depending on the density of the gas, then you will be able to separate the gases. And then we have in the pipelines, that one I've already talked about it. In the transport system, you can also apply the compressors. Then we have many of them, like in the fertilizer application, as you can see there.
So you can really appreciate that without compressors, we may not run most of the processes in an industry. As you can see in any industrial plant, any industrial process, you must have a compressor at a certain point. So that's what we had for you.
Questions? Remember, I put these sessions so that we teach each other. Why I make sure that you present is when the other guys are presenting, you should be jotting down some few points. But I see some of you seated like you are Mulekwa, without even learning anything. You will appreciate what they are saying when you reach exam. And you had them say things, but you don't remember exactly what they said. And if you could ask the second year, I've changed the way I said exam. I said things that I teach in class, not what I give in the notes nowadays. I have the power. So anyone with a question? Yes, video.
Thank you for your presentation. My question was the second slide, where the definition of compression. There. They are saying compression refers to the reduction of volume or mass of something by applying pressure. So from the video I have seen liquid entering at a low temperature and coming out at a high temperature where I show blue and red. Yes. So what is it actually? Is it compression? Is it about heating or transporting? That is my question.
So it depends. It's not about, you can use it for transportation if you have things to transport. How do you do that one? When you transport, it means you're going to get what you're going to transport, feed it in a certain tube or in the media where it's going to pass, and then you have to increase the pressure at the beginning. That pressure you increase at the beginning will drive the liquid throughout the media and the collective. That's how you can use it in terms of transportation. And in terms of heating, you can know when you compress something, the pressure, the volume will decrease. And when the volume decreases, the molecules inside will move at a very high velocity. And what will be the result? The temperature will increase, and then we shall have a heating.
Maybe you can just follow us. Is the red and blue cold and hot or low pressure and high pressure? Your color scheme in your video. Is the color scheme about?
The light blue stands for low pressure and the red one stands for high pressure. But I was trying to answer.
The red, I saw some red this side and some blue this side.
Yes.
Is the color coding for temperature or for the
For pressure.
Or for the volume, whatever you
Pressure.
for the pressure or for the heat?
No.
So where does he get the concept from the temperature?
Sorry?
Where does he get the concept of the temperature?
That's why I was relating with when you reach the volume only. And I was not looking at how the impellers were moving, but I was looking at the system which is enclosed and how your piston being applied, you are turning the piston and you're just compressing that given volume of air. So the end result will be heating. That's what I was trying to explain to him.
Second,
I was supporting their point that according to pressure is directly proportional to what? To temperature. Whenever the gas is compressed, automatically the temperature has to increase.
Thank you, Secretary.
and maybe I think you can, how do we call them? Those things which are you saw them in another's machine. When the man was calling them conveyor, but they had a similar technology. As the thing turns, although it is turning at one place, but the grooves make something will need to move to a further point, hence going out on the other side. And if you were to pump water or any other liquid, I guess that would be the easiest way to do it. If there are no more questions, make your question.
Yeah, I'm still adding about now from the video. What is the actual thing that is being compressed? Is it the liquid that is passing through?
In the video, one of compressing air. The demonstration of that compressing air.
So the impellers are the ones which compress air.
Yeah.
Well, the video, they showed you where they stopped, when the video stopped, that you can use this liquid or gas to compress something. If you remember the compressor on the hydraulic press in two sides, they switched on the machine. Then you had like a fan moving, and there was a tubing going to the piston. It is that liquid that will now go to the piston that will move the piston up for compression. And in the video they show you that at that stage, when you have now gotten this liquid and pumped it, then now you can use it for compression. We only used one demonstration of the liquid, but there are other, you can use actual force, mechanical force, like in the other compressors, like The second one says the mechanical device that compresses gas or liquid solids. Like here, it is done in this other place. But if you still want to be satisfied, you can you ask them so that they satisfy your answer. I'm just trying to cut the story short.
So, in short, where the video stopped, it was indicating that what is going to compress, let's say you need to compress like a juice from a pineapple.
Now,
There was a piston
where the video stopped actually, whatever you want to, either to transport or whatever you want to, that pressure you've generated to act upon, it's where it is put. And the rest of the process behind it is just continuous. So the pressure will keep on, increasing. As it increases, the other process, the thing you want to carry, certain thing you are using the hydraulic press, when you increase the process is continuous, it will keep on moving. That's why you saw the other thing, the other tube, small tube inside kept on moving swirl by swirl. So actually what you saw at the end was where the video stopped, it's where the other tray, the other tray was good.
Secretary, you still want to support them?
From the definition, we said that I said that compression and the reduction in the mass. I would like to know how the mass of the substance reduces when it is compressed. Because according to what I know, that the mass is constant. But according to your definition, you have said.
But in that physics, you know mass is the product of mass is the product of resonance. So when you have a reduction in one, we need reduction in the other. Convinced?
Why do they say mass is constant?
From what I know.
So you mean that if I have a huge stone and chop it into small pieces, its mass remains constant, these pieces?
Okay, from those laws, the pressure laws, they always state mass be constant. So like implementing that, the one they're showing.
No, you haven't answered me. If I have a big block like this and chop it into 4 pieces, this block here, and chop it into 4 pieces, what would be the mass of the whole piece before I chop it?
To you, the mass of this.
How would you measure the mass of this big piece?
But adding up the individual mass of the small ones in the split.
And before I split it, what would this be? How would I measure its mass?
You can use the weighing machine.
Good. So I chop it into 4 pieces. And I use your weighing scale.
You still put the 4 put there, so long as none.
No, I now get 1 piece, the quarter of this, and put it on the weighing scale. What do I get?
To be a quarter of the other.
I divide by 9.8. What will be the mass? Has this changed?
Yeah.
Okay, so if I have a sponge, okay, and that sponge, I compress it, I remove all the air bubbles. I may not change its mass, but I will change its volume. Yeah. So it depends on how the perspective of what you are doing, whatever you are trying to do. Okay, I think we can discuss these things later when all groups are done. Group 4, have you changed anything? Or I can now put the laptop with what? Yes.
Yes, good morning, members. Good morning. Yes. This is group 4. Assignment 2. going to be scared because we have 8 outlets defective, but that's not a major problem. So, we are looking at the heat exchange process and how they can be applied in the industry. So my friend will do that part, then I'll do the rest of it.
How it is done in an industry. We were lucky last time we went to the food administration. The guy tried to show us how the heat exchanger works. First of all, we are going to define a heat exchanger. It is a device. It transfers thermal energy between two fluids, or it can be between a solid surface and then a fluid. But what you have to know that the temperatures are going to be different at the two ends, maybe within the medium. Then you are going to give the types of heat exchangers. We have concentric tubes, but here I am going to look at their arrangements. We have the parallel flow arrangement. So under that arrangement, we have the two outlets. We have that outlet, and this is an inlet, and then we have another inlet there. We are going to have two fluids. We have a hot fluid, and then we have cold fluid. Under this arrangement, one enters from the other end, assuming the hot fluid enters from there and the cold from here. They are going to move, and then they are going to have the outlets. That is the parallel arrangement. Then we have the counter flow arrangement. In this case, the fluids are coming from opposite sides. You're seeing that is the out. We have that inlet there, and then we have another inlet the opposite direction. So the outlets are also going to be in the opposite ends. That is the counter flow arrangement. Then we have the shell and tube shell as in heat exchanger. This one, we have one shell, as you can see, but it has different outlets and inlets. So we have the tube outlet there, the shell inlet there, as you can see there. Those are the types of heat exchanger. Then we can go to the classifications.
Just add something on the shell and tube heat exchanger. That's the most common one used in industrial work. That's the most preferred ones. And like you are seeing in it, it's embedded with very many pipes. So you can pass different liquids at different time and separate them at the outlets. So it just depends on what you want. Currently we have computerized machines. So you just set them and you can have each pair of tubes transferring the different liquids. And at the end, the outlets also will carry the same liquids as we put in them. So this is the most currently used in big industries. Thank you.
We have classifications of heat exchangers.
Can you talk about classification? Number one, the heat exchangers are classified into two parts. We have the indirect contact and direct contact. But in the indirect contact, we have direct transfer heat exchangers, whereby the heat is exchanged between two liquids or fluids, but moving in different directions. Then in storage type, we have the two fluids move in the same direction, just like was illustrated in this type, this parallel flow arrangement, but they don't meet, they travel, they move in different passages. Then lastly, we have the fluidized bed. This heat exchanger is immersed in particles. It is immersed immersed in crushed particles, and those heat is generated in those particles, and when the fluid is being passed in the exchanger, just like in the illustration, these are the particles I'm talking about. The solid fuel fluids, then that limestone, when the fluid is passed through that, it gains heat in that limestone.
Can you use the pen like I demonstrated? If you are attentive.
So when the fluid is passed through here, it gains heat in this part of limestone. Then it produces, then steam is the one that gets out. Then the other process is, the other class is the direct, whereby we have the immiscible fluid exchangers. In this, the fluids come into contact, but the immiscible ones, they don't mix. So they still move, they share that, they exchange energy, energy. Then, but they continue moving when at a certain point they are again separate. Then we have gas liquid and liquid vapor exchangers. Yeah, my friend Sam is going to talk about the processes.
Yeah, thank you. I would like just maybe to add some more body on this diagram, which talks about the fluidized bed exchangers. Now, like my colleague has said, you find that when we put these solid fuels, sometimes you can be creative enough and use maybe charcoal. You can use something that can help you generate some difference in temperature. But what comes about is that we have an upward velocity. At some point here up, if we get an upward velocity, which is at least low, the solid particles remain fixed down here. They remain fixed. So those solid fuels feed will remain fixed. But if now the velocity changes and it is high, you find that the solid particles will be carried out with the fluid, because we remember we have they are crushed, they are light. So they will be carried out. So the difference in velocity also determines the nature of the temperature that will come, either low or high at the exit point up. So that's what I just wanted to add on. We have that part whereby we have processes in the industry that involve heat exchange process. Remember, we are talking about heat exchange and where it's applied in the industry. So we have the closed loop coolers. In the closed loop coolers, we have what we call self-cleaning heat exchangers. Remember when we visited the food and science, we saw that at some point the fall water is just deposited out. It's not used in some form. But here in the organized industries, you can have a cleaning mechanism in the industry. So what they do, in the closed loop coolers, they build large self-cleaning heat exchangers, and you find that water is always available for cooling services. But the purpose of the closed loop coolers is to avoid seawater in large number, because we have some industries that are built near sources of water. Like when you come to Ginger, they always put industries near water bodies, so that water for industrial use is always what? Available. So that they reduce on the cost of getting water. However, this seawater has a lot of problems. It can corrode the pipes. It has very many impurities. So many things go on with that water. So when we use the closed loop coolers, we mitigate the problems of corrosion and fouling of the water that we get from the sea. So that's one of the parts. The other one is the fall water steam generators. Now, in the steam generator, I have a diagram here. Yes. Unfortunately, these diagrams they are so complicated that on projection they are too tiny. But in a fall water steam generator, it is still the same mechanism of self-cleaning heat exchange system. And what happens is that it is embedded with tubes that bring about evaporation. We have an inlet channel at this point here, if you can see. And we also have a saturation pump at this point. And next to it is an insertion section. So what happens is, when that water, after passing the pipes and if someone comes out, remember it is full water, FOUL. So what happens is, we make it go through here, and when it enters through the inlet channel and goes through the pipes, there is what we call the control channels inside, and as the liquid moves up, it is around here. We find that there is some separation vessels in this system, and we have vapor produced. Now that vapor is not contaminated, so you can condense it and again resaturate it in the system and make use of it. Remember, it's a vapor, and when you condense it, you can now change its temperature and use it the way you want within the industrial setting. So that is the full water steam generator. The other one is the full water distiller. When we talk about the full water distiller, this one is an approach to produce injection steam. The third point. We may have what we call water for distillation, especially in oil industries. We find that we also equip it with a self-cleaning device, like we had for the previous one. But in this case, we are saying vapor recompression evaporator for production of distilled water from several foreign produced water. Now in this, you find that, like we had in the previous one, we have also still an inlet channel, we have a pumping motor at this point, and we have a control flow pipe at this point. Now, when water enters, at some section up here, there is a pool where boiling takes place. And when boiling takes place, like my brother, they have just finished talking about compression. Also here, there is a compressor at some point. This point has a compressor, and the vapor will be produced. There is here an outlet channel. So the whole process is that we are trying to mitigate the misuse of water. Remember, sometimes we may have insufficient water supply, or sometimes the water we use becomes fault. So we have to reuse it. And in the process, we can have those generators and the distillers being used in an industrial setup. So that one is called the full water distiller. It is also equipped with a self-cleaning device, like the previous that we saw. And at the end, we can just channel this to what we call conventional boilers that now use that water again, and that water is channeled through pipes to places where it needs to be used. Some places may need steam, so steam will go. Those that need water, that steam will be condensed and water will be taken to the place where it's needed to be used. So, the other part is about the multi-stage flash evaporators. That's the last year application. In the multi-stage flash evaporators, we also apply self-cleaning fluidized bed heat exchanger. But here the final heater uses hot exhaust gases. That's the only difference. And the possibilities provided by this is that the evaporators of the heat exchanger that uses the exhaust gases, he operates using turbines. And the only good thing with the multi-stage flash evaporator is that no chemical closing is required to prevent fouling. That's one of the advantages compared to the other industrial application that we saw. The other one is that you can operate at maximum temperature. You saw at the end there is high efficiency that is experienced with the multi-stage flash evaporators. The other one is that the distillate produced can be varied. Unlike when you are using the steam generator, that the follow water steam generator and the follow water distiller. Here in the multi-stage flash evaporator, you can vary the distillate production. The other side, you cannot vary that. I have an illustration for that part. That's the diagram. Like the first three, we are seeing that this also has a self-cleaning system, which includes gas heated, and then gas also produced out, or steam coming out, or water coming out when the gas has been condensed. So in this, you find that you may have seawater coming in from here, and after the whole process, this it comes out from this downer part here. If you can see this is all out, this is all in. So this seawater enters through, and within this system, like when we visited the food science, you saw that part of the sectional system that they showed us. It's actually, I can call it a mini heat exchanger. But if you observe it critically, it had very many pipes running around. Actually, you could see a lot of pipes and you couldn't even understand. You see how the gentleman was trying to explain, and people had so many questions and they were not able to understand. So within the system, there are so many complicated parts, but they have been organized in a way that when this steam water enters in, there is a point around here whereby it is called the heat recovery stage, and this point is called the flash stage condenser. So here, heat, the seawater that enters is heated up. Now here, you can get, of course, when it's heated up, the change of matter takes place and you get vapor, and now you get it condensed at this point. If you want it condensed. If you don't want it condensed and you just want vapor, then you have to eliminate the state of condensation at this point. So at the end, you find that here we also have hot gases that come from the gas turbine. Because I told you that unlike the first three, a multi-stage flash evaporator uses gas turbines. So you find that the are showing that from this point, the product from here flows down through the gas turbines here, and we still have the point, there is this point here. This part is the final heater, and inside it we have final tubes. So at the end of final heating, we have this arrow. You can see this arrow going up like that. So you find that at the end, this multi-stage flash evaporator stands out for amount compared to the first three that we saw. So because we are looking at the heat exchange system and how they apply in the industrial setting, these are the best four that we were able to come up with, and the last is the best. Thank you for listening.
I interjected because I was seeing what was already here. And it was about to end, but we were spending more time on wasting time.
Yeah, I wanted to explain this more. So thank you. Any addition and any question?
I'm the one to invite. I think we just the concept is that I want, for the remaining people, I want you to be innovative and try to link this more to what we saw in the Hindu food science ecosystem plan, and to make it more relevant. Much as each of you have done that one, it's like we didn't, since when we came back, we didn't really focus on the so we talked to the charcoal. And before I talk of it, I ask about the charcoal. Can you go to your definition?
Of heat exchange. Yes, we talked of thermal exchange. Of course,
as a definition.
For heat exchange process.
If you were allowed to define for us whatever you are defining, because you say definition, you read it for us and see what it means. in a cell, does it? When you are defining something and you are saying heat exchange processes involved, is that a definition?
Okay, let's call it a description.
Yeah, because a bunch of you are teachers, you need to know how a definition should be, what a description should be. If I say briefly describe and define, those are two different things. So just highlight, tell me more about chapter. I saw something to do with ashes and the doctor's chapter.
Okay,
let's go to the next diagram. Before going away, let's go back to that one. Why is it that the red, which I guess would be hot, and the blue, which I guess is cold, why are they moving in different directions?
Like we had the counterflow arrangement which we saw, that the pipes, the fluids flow in opposite direction. When we came to the shell and tube heat exchanger, in my company part I say it is the best of all the three, because the other part is embedded also in this. So you find that the flow, we have the shell inlet at this point, we have the tube inlet at this point. So as this fluid enters at this point, it saturates through. And now at this point we have the shell inlet. Another fluid is entering from here, and it is also coming in. So within the shell, there is heat exchange that takes place.
Just could you tell us how this could be located?
I would like to move here. If you look at this arc,
fine, I am okay with that one.
yes.
But I want you to connect it to what the shell means and what the tubes, how the tubes and the shell are configured. Just try to enlighten us.
Okay, when you look at the shell is the hollow, that outer part you're seeing. It looks like a cylinder. That's what we are calling the shell. Now the tubes are all running inside. That's why we are calling it the shell and tube. Because the outer part is cylindrical, and inside there are tubes running. But as one fluid enters through the shell inlet and another through the tube inlet, inside the shell itself, where the tubes are embedded, heat exchange takes place. The one with the high temperature, so which one is heat, the one with the low.
Which one is the tube, which one is the shell?
The tubes are these ones running with the red fluid from in.
But where the outlet and the inlet is pointing is actually what you are describing as being tubes, but they are saying shell.
Why we are saying shell is because now this inlet and outlet are at the extreme part of the shell, because we say the whole thing is the shell. But we are calling it shell and tube because the tubes are embedded inside.
Okay.
Yes, that's what we are trying to mean.
Other questions? Again.
Find a contribution about the countercurrent multiplier, the countercurrent movement. Will you take me back to the other? Maybe I can do that one. Countercurrent is when the two liquids are moving in. We have two pipes moving, containing different liquids at different temperatures, moving in opposite directions. The reason for that is that when, let's say, that blue pipe, if it is at a high temperature, let's say it is at a high temperature, and the other red liquid is at low temperature, the moment it enters from the other inlet, it will start gaining the temperature from that point. And as it is gaining, then the blue liquid is So instead of moving in the same direction, when they move in the same direction, they reach a point that as they get out of the outlet, the liquid which is being heated up or gaining temperature will be at the same temperature with the liquid which is entering in. And you find there you can't get, let's say if you want to increase the temperature to, let's say 37, using a liquid which is at 55. You find at the end they have reached like 28 when they are moving in the same direction. But when they are moving in different directions, the liquid which is like in the middle at 23, let's say 23 degrees C, it will keep on gaining temperature because the liquid which is entering and moving in the opposite direction is at a higher temperature. That is my conclusion.
Thank you. Actually, like he has said, if this counterflow is effective in the exchange temperature or heat, because you find that as this one moves out, the other is moving in, there is maximum absorption of energy than the previous one that we saw, the first one, parallel flow. So when you come to this one, the shell and tube heat exchanger, it combines the parallel counter, and so it becomes even more effective.
So now if I may just ask my final question.
Yes.
When we use the one which is parallel and the one which is counter, under which circumstances can I use?
Under what circumstances? Also, we may look at the cost effectiveness, but when we look at the nature of work in the industry also matters. If, for example, you want high heat exchange at the end of maybe your operation, you of course have to vote for the second one, that's the counter flow. But if you are using a machine that requires less energy, you can use the parallel flow. Just warm up maybe a fluid and use temperatures which are not high. But if you want higher temperatures in the operation, maybe for example if you're working in the food industry, which require, whereby the processing of some foodstuffs needs high temperatures, you have to go for the counter flow. But there are those that need low temperatures, so you have to go for the parallel flow. So it depends on what you are working on.
So, but you are contradicting what Gideon said. Gideon said when they are parallel, you are susceptible to having a high temperature because you are not losing any. When my hot one is coming and my cold one is coming, the hot one will keep giving the cold one until at some point they get a given temperature that could be a bit lower than the hot one, but not so low. Whereas when they are counterclockwise or counterflow, you are having the warm one is losing the cold one and is doing so towards the other side. And I'm not sure whether...
No, but it depends on the temperature of the incoming hot liquid also, because if they are counter and they are moving in opposite direction, you find that as this one moves and this one moves also past it, it is absorbing everything that goes past. Now, if they are also moving in the same direction, depending on the temperature with which the hot fluid was let in with, remember they are moving around each other. But remember, as they move, there is also heat loss also to either the tube metal, by the conduction.
Because the heat from the tube metal is taken as a constant.
Okay,
of these two moving in the same direction,
yes,
and moving in counter directions, where do we find a higher temperature?
Okay, when they are moving.
How can I call it? The average temperature at the end of the day. Where in which of these two systems do we find a higher temperature?
The parallel flow.
Parallel flow.
Yes.
Why?
But what I'm saying,
because if the liquids are moving at the rate and the constant rate, the counter flow, and then they are also moving at the constant rate in parallel flow, why should we have a higher temperature? Because it is not that we are putting in a liquid And this liquid not salt, they will flow at comfort without any mix. The other one is coming at a different temperature.
Yes, you have something to say.
Yeah, I think to hit the last nail on the coffin. Counter flow always. We say counter because we use it for cooling mainly. Yeah. One substance the one liquid has to be at high temperature and the other one low temperature.
Both are different temperatures.
Yeah, they should be at different
The
temperatures.
red layer,
That's why we call them.
Listen, the red layer and the blue are coding for one being cold
And one being
most likely the blue and the red one being cold. So
Okay.
in both scenarios, you have two liquids which are different temperatures. Whereby one is higher than the other.
Okay.
So you cannot say countering means that they are different temperatures. Both of them are different temperatures. Counter is that they are moving in different directions. Parallel, they are moving in the same direction. Parallel.
Okay, make it clear the effect. In counter, one liquid leads to the drop in temperature of the other. Because if you have counter flow, one liquid will come with a lower temperature, very low, and another one is high, the one you want to cold. So at the first point of contact, there is high temperature gradient, and hence there will be the flow of heat from one liquid to another. Let me say at every point of contact in counter flow, because they are flowing in different directions, at every point of contact there will be high temperature gradient. But with the parallel flow, time will come when both the liquids are almost at the same temperature. So parallel flow will lead to there will be increase in temperature in both of the liquid to a constant temperature. But in counter flow, there will be a drop in temperature in one, which was the initial high. I don't know what.
Okay, let me now, before you comes in. Here we are. The liquid has met the hot one here.
Yes.
And started losing its coldness as it moved. Remember, this one is not something is cold. This is hot, this is hot, this is cold. So I have met the hot one here, and I now start losing my coldness. You see, I'm heating up, and I'm heating water.
Yes.
So this is counter.
Yes.
So how we get to it? Am I becoming water or water? See, I have coming. This is hot all through. It is coming on is hot. I'm coming on and cold. I start losing my coldness, and I keep interacting with water. Do I end up? This week this is I don't even guess. If you can say it, I will let you now have a debate on your own.
Yeah, what I wanted to say was supposed to clarify on what the meaning of counter flow is. Meanwhile, the other one is parallel. They are all happening inlet from one direction and they go to the other side. Counter is that they are coming from the opposite direction. The other one comes like this and the other is going like this.
Yeah, we must agree on that. So, that one I would agree. We are now on the issue of there's some effect of the interaction of these two liquids. They are moving in different directions and having different temperatures compared to when they are moving in the same direction, still with different temperatures. But okay, what we should realize is that we are not having, if you look at that break, that kind of break in the diagram, it shows you that it is not just a 1 meter of reduction. What we are arguing about now is an argument of here and then up to here, then water and this. In the heat exchange at the other side, you saw a stream of, even when you look at the back of the fridge, the group 1 of last assignment, at the back of the fridge you have a stream of the tubing is too long
that you have that amount of interaction. So even in the heat exchanger, you are having a lot of, and if you look at it, you are not looking at the fluid or a liquid being put in and then you stop. It's a continuous process until when you are satisfied of what you want. If you want, and I told you, if you are treating juice, you heat it up until when you are sure it has reached a given temperature. So we may not really achieve this theory. We are saying that when this one comes, it reaches, and then the temperature of this is higher than this. You are achieving an exchange until when you have normalized at one point. And you can choose whichever method that you want to use. But you can debate about it in your free time to get a feel. And I'm sure when you are doing the assignment 3 in the graph or the experiment 1, you'll be able to get it because our time is tight. So I guess group 2 or 3, I don't know which one is which. Those who guys have, I will have to move mine. I will thank you for your effort. But as a group, you need to do a lot in understanding what other groups do, because there are no more group works. As individuals, you must make sure that your assignment 3 is well articulated. Assignment 3 is individual work. You have to hand in one by one. No bringing in book Please, if you can make a point clear by rushing through it, do that, so that I want us to finish. I don't want to go into lunch time. Patience. Exercise patience.
Okay. Good morning, members. Okay, we are going to look at vacuum pumps, vacuum pump systems. And since time is our enemy, we start with the vacuum pump introduction. We're going to look at what a vacuum is, what components, major components make up a vacuum, then how to measure pressure, mainly in vacuum, because in a vacuum pump, pressure is the most important thing. So, ladies first, you have to tell us what.
We have to look at the definition of a vacuum, where a vacuum is any space without matter. Like, it comes from a Latin word, vacuus, which means vacant or void. Yeah. Vacuum, it became a various industrial tool in 20th century, where like there was an introduction of light bulbs and vacuum bulbs in the industry. So I can also talk about the components of a vacuum system, where a vacuum system, it has a pump. It has a pump which is connected to a chamber. It's a pump that absorbs air in order to create a what? Like to produce a vacuum. Then a chamber, it contains the apparatus that requires use of vacuum system. Between a pump and a chamber, there are tubes, fittings, that are required for a vacuum system to operate.
All right, we maybe put more light on what she has said. We say a vacuum is a place without matter. So if a place has no matter, it means low is at low pressure. So if there is low pressure, it means there is that maybe sucking effect. That's why people who boats, those people in the villages use those long strays to suck the air so that they create the vacuum, which will be substituted by whichever alcohol they are taking. Then if you take a soda, it's still, that's how vacuum work, isn't it? And the other time when we were at our one and only industry, then the campus, we saw how they created a vacuum in there. I mean, our had had something. They gave her the piece.
Even yours took one.
So where they put that polythene in order to create a vacuum, that's the vacuum chamber. So the other components down there, we have the pump that creates that sucking effect. So it is transferred up to the vacuum chamber, whereby each evaporators you want to, maybe you want to use it for dusting, is that vacuum chamber where the pressure is created. That when you put something next to that vacuum chamber, it can suck it out. Second, we'll talk about the measurement. How can you measure the pressure?
Now, my colleague has talked about the components that there is the vacuum pump and the vacuum chamber. But in order to create a vacuum, there must be a pressure difference between the vacuum pump and the chamber. Therefore, you need to measure the pressure such that the pressure at the vacuum pump is greater than the pressure in the chamber, to allow the flow of air, the continuous flow of air. And the measurement is normally done by, it can be done by the Gordon gauge. So we can also talk about the means of producing the vacuum. We have two ways you can produce a low-grade vacuum and a better vacuum. Now, for a low-grade vacuum, we use a piston. It means that the low-grade vacuum, the vacuum which is produced, is not good, such that when you try to compress air, some air, instead of moving out, it can create a dead space above the piston. And you wanted to remove air, but some of it can cause a leakage, such that vacuum which is created is a low-grade vacuum. Another one, to produce a better vacuum, here they use what we call a rotor, something which rotates. Now in that rotor, when it is rotating, it tries to blow out air altogether. So now, in order to allow continuous rotation of that rotor, it must be oiled altogether to reduce the friction.
So let's look at some of the terminologies used in vacuum systems. One of them is mean-free path. Mean-free path, what you know about it is the minimum distance between collisions. Minimum distance traveled by molecules before colliding with another. So if we can't talk about pressure, we're talking about mean-free path, because if the number of collisions are very many, then always pressure will be high, because of that pressure is always the force per unit area. So if you're going to vary pressure, if you're going to reduce pressure, of course in the vacuum you have to reduce pressure, then it means we are making the mean-free path to be longer. So that before this molecule collides with the other, it has traveled some appreciable distance. So there will be low pressure and there will be a tendency of vacuum. So to have a perfect vacuum, then you should have not even a single molecule of air in it, and you vary that using by increasing the mean free pass, or by eliminating the air. Then the other one, we talk about the flow. Of course, as we lower the pressure, there will be the fluid will be undergoing different types of flow. Of course, you know that when the molecules are very many, there will be a lot of viscosity. It will be having some tendency of viscosity in it, and you know that when it's the viscous fluid, there will be always a lot of resistance. There will be some sort of turbulent flow when the level of viscosity is high. But as we keep on lowering pressure, it will end up being tending to molecular flow. And molecular flow is not turbulent. It can be a little bit laminar. So, what are we talking about all these things? Because these are the major terms that are being used when you're dealing with vacuums. So I think secondly we'll talk about backstreaming, what backstreaming is. But before it does it, I'll just give you a hint, like you talked about the beta and the what? Low grade, yeah. Low grade, these are like we've seen these pumps at home. The one used for those who have bicycles for carrying air in the villages. As you try to pump, sometimes the molecules, not all molecules, will be forced away. So as you try to create a vacuum, sometimes some molecules will tend maybe to flow back as you try to press the piston and flow back to your vacuum. So that's what we call backstreaming. Sometimes as you tend to create a vacuum, some molecules tend to come back into the system. That's backstreaming.
Now, backstreaming, it occurs. Remember, I told you that in this rotor, we normally put the oil to allow the rotation. Now, and you know that whenever there is some friction, it causes a heating effect. Now, the oil which you have put there may evaporate. Remember, we are trying to remove the gas. But this oil, as a result, it can reach its vapor state or steam point. So it vaporizes and go back to the vacuum. Hence causing that going back to the vacuum is what we call back streaming, and it can cause contamination within the vacuum system.
So I think in the interest of time, we can just proceed to the next part. We shall look at maybe conductance of the tubing, outgassing. We can come to that one for special attention if you're telling it. Then mean free pass, we talked about it, flow, so there, backstreaming. Let's look at application of vacuum. I think some here we talk about that.
Yeah, yes, when we talk about the applications of vacuum systems here, vacuum systems are applied in cleaning systems. For example, when I want to dust a machine, when I want to clean a machine, when you are cleaning machines, you make use of the vacuum systems. I think we have seen some of them. We shall show them during the videos we have, whereby some people are using vacuum systems to clean, as in to remove dust from those machines. So that is one of the applications of the vacuum system, because the vacuum system helps to create that vacuum, which again brings about pressure and then cleaning that dust off that machine.
Okay. The other one is let's talk about vacuum cleaning. You know that it is sucking effect. There is sucking effect in a vacuum. After removing the air, there will be a tendency for matter to rush into that space, to go and occupy that space. So if I want maybe to dust this surface, I may just bring some sort of vacuum, pump out, and I pump, it is suction effect. So when I bring a vacuum next to this, that it will keep on sucking the dust, like sucking the particles of the dust from maybe the computer. Sometimes we use it for cleaning the walls. You just pass it around and keep on sucking off the dust. We tried to download some video, but it failed to play, I think. Then,
please try to be quick. We are fighting time.
Alright. So ranges of vacuum pumps, depending on what you want to use it for, you can make treat the pressure. Depending on what you want to use it for. If maybe you want to use it in a push, of course you looked at one that was being used for pushing what? The hydraulic press, yeah. The one we saw in the food science, the one that we used to push to maybe squeeze the fruits, the juices out of the fruits. It depends on what load you want to use it for. If it is for carrying like a vehicle, then you use higher pressures, like here we have 10 to 100 and all that, to keep on varying the pressure. So effects of vacuum systems on humans, of course, one of them is death, and sometimes they lose consciousness. Because there is a video in which I watched somebody, a vacuum sucked all the intestines and everything from him, because he made a mistake of sitting on a vacuum sack with suction effect and sucked out everything through one of the openings. So it can cause death if you play around with it. Then types of process vacuum systems, we have dry pumps, we have rotary vane pumps and liquid rain pumps. This is one of these are, you can see the gauges. These are used for measuring the pressure in the vacuum. And this is the rotary vane pump. There is one that is, okay, it has valves, and this here is a motor that tries to maybe makes the air flow out and creates a vacuum on one side. This is one, I think I can use this pointer. This one here is the chamber. Then you have a motor somewhere here. Then on top of this, this motor we have, this is the gauge that is used to measure the amount of pressure. Then industrial processes that require vacuum systems, cleaning machinery, purification, in order to a gas somewhere, you can just bring a vacuum and sucks out that bad gas or bad smell out of a certain room. Then drying processes such as crop drying, you can also use vacuum. Refrigeration processes, sealing, this one is really self-explanatory for those who got the other cereals, regimes. I think that's all.
That means you may need to upload another one because what you uploaded has is missing a couple of words.
All right.
Including the ceiling of the gas
Yeah, we have
those who have questions, please.
Yes, Professor Lee.
My one is about how is the vacuum system used in refrigeration?
How? Okay.
In what?
How is the vacuum system used in refrigeration?
Okay, to talk about that, we say first of all a vacuum. If you're talking about a vacuum, you're lowering pressure. And from pressure laws, you know that if you lower pressure, pressure is directly proportional to temperature. If you lower the temperature, the pressure, you're also lowering the temperature. So that means automatically you're cooling something, and that is the process of refrigeration.
But in your definition, you say a vacuum is anything that has no matter.
Anything that has no matter. Yeah, of course you have to know how temperature or pressure is related to matter. If you have very many molecules, air molecules in this, you know that pressure is forced by air, isn't it? If you have very many molecules in a given, let me say, chamber, there will be very many collisions, isn't it? And at every collision, there will be force will be exerted, isn't it? And point area. If there are very many molecules, there will be very many collisions, hence there will be higher force, and that will be higher.
So if I have a region where I have only one arrow, would I have, can I achieve a vacuum?
It can't be vacuum, but it will be at low pressure.
As you explained that, how come I'm not hearing one presentation of which group were you?
Group 2.
Yeah, group 2, you got a comprehensive explanation of the vacuum system. How come the concept of cooking or lowering the boiling point of some of the foodstuffs we told about us, how come you are not hitting on it? We had that thing like a pot where we changed the vacuum, whatever, reduce the pressure and then make the heat, the boiling point of the cooking, happen quicker. Anyhow, this shows you, this presentation show you how you can easily miss out a point.
Yes,
that was really crucial.
Very important. Yes, no doubt.
So I would like us to end it here and ask for the other group to come and also share with us. The reason I'm doing this is that much as I'm going to put them into PDF and everyone is able to read them, but you will be knowing what people are trying to talk about. Not that we are just...
Good afternoon, class. We are group 3 is the last. Our presentation is about lighting assessment, and on the table those are the group members, and I'm the discussant, and then my colleagues will join me. So not waste time, I'll go ahead and define lighting assessment, of which lighting assessment refers to in simple terms, the critical examination of the work or of the condition of the workplace in terms of light, or according to our definition, is careful examination of the lighting condition in the work environment. We know the work environment doesn't mean only the industry. We have industries, can even be a class, can even be, but now our main direction of the lighting assessment is an industry. The lighting condition there, and this is what the purpose or as why we carry out lighting assessment. There are various reasons to include the following. The first one is to help identify the potential that's arising from the prevailing lighting conditions in the workplace or in the industrial setup. For instance, like if you go if down there, when we were there, when we went there for our tour, you saw what was in the place. We had very many openings that were allowing in light, but assessment comes in a way that the lighting which is there is not favoring what is taking place inside the industrial setup. So it calls in for the assessment. If it is okay, it has to be left kept on, or if it requires adjustment, then there should be adjustment. Then there are levels to assess risks and identify hazards. You have to assess the risks, because risk and hazards are related in a way that a hazard is anything that can cause harm, and a risk is a chance that someone will be harmed by a hazard. So we have to assess these risks and find out what extent are they going to cause harm and how can they be mitigated. And then the other one, it helps to identify who may be harmed. For instance, now like if you assess cause, we know that this lighting have effects on how people work in another setup. For instance, you're working in any environment. Of course, you have problems with your eyes. Or in case there's too much light, how is it going to affect the workers? And then the other purpose is it helps to evaluate the risks and decide on the improvement measures. Of course, after evaluating and assessing, you must know which specific measure or mitigation am I supposed to use to overcome this problem. And the other purpose is to minimize maintenance costs. For instance, if I come and, okay, you were there at food science, you saw how their lighting was made. After you have done your lighting assessment, of course, you have to install. After installing what is required of you, it will not guarantee that almost after every day you will be performing and making replacements. For instance, if we are using bulbs,
and maybe all of a sudden after every day they are blowing off. And so now this time I'm going to employ windows during daytime, so that will be have continuous supply of light. Of course, we will not be incurring costs, and we have minimized costs. And the other one is energy and cost saving. How is it energy and cost saving? Light, for instance, light uses power. I know you are all well familiar with that. It requires maybe wiring and so on. But now here, for instance, if you're using windows to supply you with light, you will need very little lighting systems or bulb. That's maybe only at night when there's little light provided by our environment, and that is the sun or the surrounding. So that is energy saving and costing. Of course, even the power will not be used. That is in terms of energy. And the other is achieve greater efficiency. These are the results of the performance of the workers. Of course, if everything is well provided, you realize that people will perform to their maximum. Then hazards that call for assessments. As I said before, a hazard is anything that can cause harm to a worker, and they are related to with the, what we call a risk. A risk is a chance that someone will be harmed by hazard, or it's the probability in mathematics, the probability that an individual will be harmed. Then we have improper lighting installation, maintenance, replacement, and disposal. This can be a hazard in a way that it may be affecting a worker in a way that a worker may not be performing his. For instance, if you have lights installed, for instance, you're supposed to read, but maybe the light is placed far away, that the light that's reaching you on the table is insufficient for working, or is not enabling you to see what you're meant to see. For instance, in the labs, you have chemicals that you need to really see, that maybe this is a dangerous chemical and you have to be what? To take care about it. But the lighting which is there is not allowing you to see it carefully. Then we have improper selection of emergency lightings. Then we have lighting effects. The lighting effects, we have very many lighting effects. We have glare, we have color effects, we have, and they are going to be discussed for you, we have the stroboscopic effects of light, we have radiation, infrared, because all these affect the workers. Then we have incorrect lighting design. Lighting design, we have very many lighting design. For instance, we have positioning of light. For instance, in an industrial setup, there are instances where we're supposed to have maybe overhead lamps, which are supposed to help light reach distant places for workers and for protection purposes. And also, light that maybe just need to cover within a short place, maybe for use in a room, but incorrect lighting design may also ask for or seek for, call for lighting assessment. Then we have the approaches to lighting assessment. Basically, we have two approaches, of which you have one which is by checklist and the other one is by measurement. The approach by checklist is a person who is concerned or the expert in the lighting department has to go in an industry, check out what is the lighting requirement that is required, and then he notes it down, and then after he comes and fulfills that. For instance, maybe it is like a room and says it is a reading room. Yes, it has maybe it is just by guesswork. Assume it has to be like this, then he has to fix. Assuming it is a spoiled lamp, he also has to say that lamp is spoiled, it has to be what? Replaced. And the replaced, that is assessment by checklist. You just see what is missing and then put it there. Then the other one is assessment by measurement. Here the person does the actual measurement of the lighting requirement of the industrial setup. And the person must have gadgets to help him come up with such measurements. For instance, the most common parameter that always used in the measurement is the illuminance of the room or maybe of a given place. And the device that is used for that is called a lux meter. That is used to measure the luminance of the room. Like if you have, that is by assessment and then by checklist. And then the other one is just a simple pick
Because like assessment, you see this guy and this lady, they are trying to look up the wall, and they don't look up the wall and they are trying to say what is exactly required, and then they are noting it down. You see, they have some things are noting down. And then the assessment by measurement these guys are having, like, if you look at that's a laximeter, and there's another gadget that is holding to help him receive the intensity of light and then compare with the exact requirement that they are supposed to incur. Because, like for instance, if you're working on a table, there are some specific measurements that you have to measure that what is the distance between where you place your light and where you're working from. Is it normal for the eye to operate, and so on. So from there, I call upon my friend again from there. Thank you.
All right, thank you. So we're just going to give us just the way the measurement is done using a laximeter. A laximeter is, like I said, the measurement is done for purpose of verification. I've already cited out that. Then we're also saying that the parameter used is illuminance. So what could illuminance be? It refers to the amount of light falling on. It refers to the amount of light falling on a unit of area of the work surface. So it's measured in units called lux, which is denoted by Lx. And just to take a small look at that picture, inside that room, we have some sources of light up, and also the windows and some table lamps, just giving us an idea of how light may be distributed in different forms inside a room. So the measurement, the laximeter looks like that. We have the part that displays the reading and the sensor. So just like it is demarcated from there, the sensor is a part that is sensitive to light. Then it has that wire coil such that you can stretch it to whichever distance. Meanwhile, you're holding it, and it gives you the reading. So when we look at when you take a case, maybe say a wall in a place, now this place, we need to take the measurements of to take the luminance of say a wall. We need to subdivide that area in portions, possibly squares, a number of them. Then you use that sensor, you direct it to the center of every square and record the measurements as displayed on the machine. Then you average it. Now what you get is what we take to be the average of the luminance of that work area. When you also look at, it may not be a wall or it may not be a flat surface. We can also have some other things. So in this case, say it could be a machine. You can identify just 4 points where you can take measurements from. Say maybe this is the place and this is the machine. I put it at this point, the other point, this point, and here. So I get the measurements, average them, and at each point have them averaged to get the average luminance of that working position. And the average is then compared with the optimum average illumination recommended for a task. It's just that we didn't put it here, but there is a table that contains the average, the optimum average illumination for every task. I think we shall also include it in the PowerPoint we're going to send up next. Now when you look at such a thing, that guy is operating that thing, but from different sources of light, he's getting a reflection direct to his eyes. So if we took measurements on that thing at different positions, then we can be in position to tell this is the minimum amount we want for this activity, and he can be in position to put on, to use any kind of protection measure. As you can see, the guy is putting on this. Yes, the goggles. Examples of such places. If you've seen places where they are welding from, you always get those guys when they are not holding that thing too well, they can first lift that thing up. But when they're going to put it down, they put it back. It's to avoid such dangers. We have said it is we measure luminance in this assessment, but there are also other parameters that we can measure. So depending on depending on what you want to measure, the instruments are out there on the market, and you can just buy the one you're interested in. You can also measure illuminance, that is the amount of light reflected from the surface. And the units is candela per unit, per square meter. As you can see from the picture, we have just light which is reflected. Then the other one is contrast. That is to show us how clear or how dark a given surface is compared to the other rest. So you can see the first one is dark, then the other one is bright. We can also have cases of improper lighting being reflected to the eye on a surface just because the two surfaces have different contrast. So the relationship between the brightness of an object and its background is what we call the contrast. The luminance meter is also used here to measure. So, and the average contrast should be above 0.5. That is for a normal working environment. And we have the formula how we can find the contrast. It's the luminance object and luminance of the background divided by that of the background. We also have reflectance. As you can see, light falling on a surface and then reflected. The reflectance is expressed as a percentage. The light falling in, you can measure with a sensor that this is what is falling on the surface and this is what is leaving the surface. Then you can put that in that formula and you have the reflectance. So it's the ratio of light falling on the surface to the other, the light reflecting from the surface expressed as a percentage. The light meter for reflection is used to measure it, or by comparing the surface of interest with color chips of no reflectance. There are also the color chips. These are just some kind of it is a chart that can be provided by the experts that once you have a surface which has this kind of a color, it means it will always have this kind of reflectance. If you have the other kind of a color, you can have this amount of reflectance. So in the case where you don't have the instrument to take measurements, then you can just look at the surface, tell its color and compare with what you have in the chart. Managing the health and safety risks from lightning in the workshop. So we have, we can manage them by controlling, we can manage them by monitoring, or even by doing risk assessment. My colleague did explain so much on control, monitoring and risk assessment. Then the steps normally followed during the risk assessment. We are saying we're identifying the hazards in the workplace to see what may cause harm or injury. In this case, it is harm to the eye. Then the other one is identify who might be harmed. Because in the setup, if I need this kind of light, not like for the welders, for those guys they can stand that light because they have the measure. But for someone just passing around, that person is more endangered than the person who is what? Who is working in that environment. So in this case, the person who may be harmed is the passersby. And in that case, we can say, we advise people not to pass by such and such an area. Then you can also identify, you can also evaluate the risks. What is the measure of such a risk in case it's to happen? Then after that, we do record the findings and the review of assessment regularly. We are saying we cannot only do when we are setting up the industry. Rather, it is always a requirement that you have to keep, because along the way, as the operation continues, something may change at certain point of time. So it's advisable to always keep doing the assessment. So lightning effects, we have color effects. I think let me invite my...
I think I was about to mention, what are the other two guys? There's actually three. Mayanja, Senkwana, and Didi. You're not saying anything. You are comfortable. So, can one of you go and push up the lightning effects and something that is additional? Video. That's what I'm asking about. Go and tell us. Quickly, because we are working too much time. And is taking notes.
Now we are looking at lighting effects. What are the effects that arise from the lighting? So one, we have color effects. For example, we know that light from the sun or light from any gadget has a certain color. But from what we know, the white light contains different colors. So light effects in an industrial setup, we may have a room, as they have talked of, luminance, the reflected light. For example, if light from this bulb falls on this wall, then what would be reflected from the wall? And when it falls into your eyes, if it is a red light that has been reflected, now how is it affecting your eyes? That is about light color effect. Then we go to stroboscopic effect. So that one.
No. You let him explain what it's like. We are not going to agree. Because when you read this one, before coming to present, you are supposed to have strong relation. You are supposed to be owning the law. So, you don't know how you are going to do that. Please, we are hungry. Tell us what stroboscopic effects are. You don't know a stroboscope in senior 4. This thing which turns and then you see many colors. When actually, which has many colors, and when you put it at high speed, it becomes white. You've never heard of it?
Yeah.
You don't know it?
Yeah.
Okay. Nobody can. Okay. Oh, but my answer.
Concerning.
Wait. My answer about the couple. Can you just throw all the points there? The Vika, the varying reflections, the radiation and infrared radiation. Yeah. So my answer. Tell us about the Vika. No, so who did the work?
No, they just added this. Because
Fine, but who did the work? Who did the damn work? You guys, you have to be serious. In one or another. During my time here, we would Xerox. And after Xeroxing, you would have to either photocopy or copy as we are not there by our time. So you would have to photocopy with hands and make 2 copies if you were a really bad road. So we will hand in and start reading what you Xerox, because most times you will have inside or come in a test. So it's stupid to get a 9 in a Xerox assignment and then the same numbers come in a test and you flop. My reason of thinking group work is to work as a group. Encourage group, encourage teams, which have not seen, okay, or not one man show, you do the thing. And then maybe they can learn from it.
Okay, this is what the effects of light. We're looking at effects of light on our normal operations at the workplace. And the first one, we're looking at the color effects. We realize that the lamps we use, including the sun, the light that it produces can be divided into very many different components. But now in industrial setup, you realize that these colors, some of them, as you look at them, you realize that as you are observing, there are some colors which may go unobserved. And the colors which may go unobserved may cause harm to their members or the staff in an industrial setup. Then the stroboscopic effect, this occurs as a result of the lamps, okay, the AC lamps that we use, they have varying oscillations. The current is varying, and realize that it produces the effects. As a result, we realize that some colors, some colors will also not be observed, and because of the eyes of the workers in the industrial setup. Like we're giving us an example of the other thing which was rotating, and you realize that you don't see other colors. As it's rotating, the color is not rotating. So the lamps, they are being operated by AC currents. Which AC currents are?
Just tell us the points you have.
Okay. Then the flickers, you normally see them as a result of, you see them from the edges. For instance, if during eclipse, you have always seen the eclipse, you realize that, for instance, when the moon is almost covering the sun, you realize that at the edges, there are some bright spots. But this
before you go further,
yes.
Flicker is don't bother yourself. No one is going to say anything, so listen. You know what I'm explaining. When in heat and not heat and thermodynamics, but in your A level you need heat. And when you studied about ionization, you were able to be told of these lines which happen in the tube. And then you get dark spots. And you have seen some tubes flickering. Actually, the tubes, before we changed the tubes near the nut spots, they were flickering, going on and off, That's what the flicker is all about. So you shouldn't have in an industry any lighting that is flickering all the time. Please just run through. I know you did not, in your souls, you did not understand this, but show them to us. I come there and then I conclude the session.
Okay. Then I look at the infrared and ultraviolet radiations. These are emitted as a result of this light effects, because these lights that the lamps produce, they also emit infrared and ultraviolet. And as you know, ultraviolet is dangerous to our bodies because mutagenesis, and as well, infrared is that effect of heat that is produced and can also affect our. Then radiations, these are mostly concerned with the sun, or the light which comes from the sun, which affects also us in various ways. Then the veiling reflections are just light being reflected from different surfaces of the building. Then to wind up concerning the issue of, we're looking at how the assessment is done on a horizontal surface like this. We were talking about the walls, but it is done on a horizontal surface on a work plane. For instance, if this is a room, measurements are made all over the whole room. Then they are divided into small squares. Then the height from the bottom to the surface where the lighting system is going to be placed is measured. And normally is taken to be around 0.8 meters. 0.8 meters around 80. Like for instance, if the table has been up, something like 0.8, a minimum of that. Then if the room has not yet been having those work planes placed there, then someone has to estimate and then considers a horizontal distance which is equivalent to that distance. And I think with those, thank you for listening.
Are you put together?
Wait. Okay, glare, this is like, this what normally happens, you realize that there are some people which are having too much light intensities. For instance, if at night you are walking, then all of a sudden someone flashes, you see a car coming from in front of you, more especially if you are rain in that evening and you realize that atmosphere is cool. You realize that as you look at that car, you realize that there is, near the lamps of the car, you realize that there is a very bright spot, and these bright spots are scattering as the intensity disappears. For instance, if this happens in an industrial setup, you may fail to see. And at the end of the day, you find that you've got an accident in an industry.
Okay, questions? Yes.
I have some simple correction on the effects. Can you go to the effects?
Effects. Lighting effects.
Lighting effects, yes.
You can be asking us, or you want to see it first?
I want to see it first. So on the lighting effects, I think you looked at it at a point of being hazard all the time. All the points you're trying to explain them at the view of being hazardous to a human being. But for me, what I see is, if you look at color effect, you know this, we have different objects of different colors in the industry. So for me, I would say effect of light. If I have a green, maybe more lights, then the red light here, I may misjudge the color of that maybe that instrument or just because I've used different color light. I think that's the effect. But don't just look at it as this color will affect your eyes like that.
Okay, you are having an open thinking, but as far as our research is concerned was to look at what effects may bring about lighting assessment. And for lighting assessment to occur, it means there must be some negative effects that might have occurred and you want to mitigate it. That is all our concern. But we know light effects, of course, not all of them are bad. But we are looking at only the negative side and we are looking how they can be mitigated.
I'm cutting this story short.
Okay, all right.
Any other question?
I just want to talk about stroboscopic effect. In industrial setup, we have moving parts. I'll talk about the few ones we know, especially the moving belt. That are part of the machine. If the light is not good, the worker who operates that machine may look at that belt moving as station and may be tempted to touch. And the process gets an accident. So light should be considered because if it's not rightly placed, it may prove to be a potential hazard to the workers, especially those running those machines with turning parts.
Any other concern?